Yes. So the next thing we want to do is you want to look at how we simulate this communication channel for dishonest verifier, which is quite tricky. And before we do this, let's start with some general definitions. We want to, so formally, an interactive proof system consists of two parts. One is the algorithm of an honest prover who knows the secret, and we have some public information Y. And we have the algorithm of the honest verifier, which is V usually. Now, with V star, we denote an algorithm of a possibly dishonest verifier who does strange things. And this generalizes the verifier notion. So the dishonest verifier could inject some kind of questions into the answer. So here in this example, it's not quite obvious how to do that, but in general, this is a huge problem. So the proof system also includes the interaction, and we assume that these are probabilistic polynomial algorithms. So that means two things. One is that we have polynomial runtime, depending on Y. The other thing is that we're using random bits. I think from an intuitive point of view, randomized algorithms are pretty much standard somehow, although we do learn some kind of randomized algorithms in other lectures. Usually, for example, if you do AI, you have maybe some particle algorithms, or you have neural networks which start with a random configuration, then you already have a randomized algorithm. Or if you have some optimization problem, you start with some kind of point, which is a random position, then you also have a randomized algorithm. So you don't notice this anymore, because if you need some kind of general state, when you inject randomness in and this usually helps to solve things. Now, because, for example, 3 random points are not on a line with probability 1, which is also helpful. You don't start with strange initial conditions. But in cryptography, we need this all the time, because we have to inject randomness in the algorithm in order to exploit the full complexity of a one-way function. But what we actually want to do is we want to look at the transcript. And the transcript are the messages sent. So you have some prover, you have some verifier, and you have message 1 and message 2 and message 3 and so on. And there is no restriction on the type of message that we send. The important is that we have this going back and forth. And if you have 2 messages sent in one direction, then you just combine it into one message, of course. So we have some messages sent from a prover to verifier, and some messages to verifier to prover. And in this notation, it could be also that the prover starts with an empty message and the verifier starts with a message. So if you look at this transcript, then this has somehow the whole information of what is going on, because the internal states are, what the verifier sees are the message from the prover and the public information. So from this transcript, the verifier accepts, if a verifier accepts, then it's all in this communication. There's no hidden information anymore. And we say it rejects with the verifier rejects. So we can look at the messages and find out whether this is accepting or not. So the transcript is not necessarily determined by what kind of public information, because we have this random bits, and the prover and verifier could also have random bits as well. So that's because they could choose random numbers and send it around. Now, what is perfect zero knowledge? An interactive proof system is perfect zero knowledge if there's a probabilistic simulator which has expected polynomial runtime, depending on Y, and outputs an accepting transcript, so these kind of messages going back and forth, in the same probability distribution as it was generated by the honest prover and the probable possibly dishonest verifier V star. So if this can be reproduced by some algorithm, and you do not, it doesn't mean that you get exactly the same script, but every possibility of communication is reproduced with the same probability. So that is what we claim, and then you have learned nothing, because this mother-in-law, what she said to you, I told you so. You don't know anything, but I told you so that this will happen. So if you look at a conversation between two persons sitting on a bench, and you sit there, oh, interesting, and somebody says, well, I could have produced this communication on my own, and it could make the exact communication with the same probability distribution. You shouldn't, it actually didn't gain any information because I could have told you this, and I don't know the secrets of this communication. Then this has no information. And actually you have learned nothing because you already have an algorithm which produces the same output. And that's why it's called perfect zero knowledge. And there are not many problems which really have perfect zero knowledge. Or maybe there are. Which kind of problems? What can you prove with perfect zero knowledge? And because you could actually fake off communication coming up. Now, what is a simulator? So the simulator has no access to the secret X. So it doesn't have anything. And it cannot follow the algorithm of P because it doesn't have access to the secret. So the simulator has to do something else. If you look at this type of algorithm, we have a Las Vegas algorithm. Who has heard Las Vegas algorithm before? Yeah. So what's the fellow of a Las Vegas algorithm? Yeah, there are two kinds of probabilistic algorithms which are efficient. One is called Las Vegas, and the other one is called Monte Carlo. Yes. What's the difference? So Las Vegas algorithm is always correct. Could take sometimes longer, but it has expected a polynomial runtime. So expected runtime is bound on the input length, polynomial. Monte Carlo is an algorithm which has a probability that it could fail. Yeah, for example, if you look at the prime number test that he had with Solovay-Strassen, and he says yes or no, it's a prime number or not, then this was a Monte Carlo algorithm, because there's a chance that this says, oh, this is a prime number, but it's not, and the composite number was always right. So this is Monte Carlo algorithm, where you have a probability of failure. You can repeat a Monte Carlo algorithm over and over again to reduce the error probability, but it's still there. Our Las Vegas algorithm has always zero error probability. So that's the difference between. From a psychological point of view, why would you call the one Las Vegas and the other one Monte Carlo? I think you have to get into the Americans' perspective, because if you're gambling in Las Vegas, you're still in the States. If you go to Monte Carlo, it's France, it's, Europe, and anything can happen, That's why the Monte Carlo algorithm has. So that's how I see the difference. Yeah. So it's not even a democracy in Monte Carlo, I guess, because we have a duke, who hires movie stars. Okay. No? Not the democracy? Okay. Anyway, so something you have to remember somehow, because we're two gambling towns. Okay, so now we need that S has a decision of a verifier for some reason, because it could be dishonest, so it doesn't adhere to a protocol, but has no access to a protocol of P. So even the dishonest verifier doesn't know anything. And now let's prove that the Fiat-Shamir identification scheme is zero knowledge. This is a proof. So what we do? So we have, this is the set of transcripts where we have A, E, and B. And the transcript simulator does the following. Basically, it does the same thing as a cheater. We start again with B, random B. Then you choose a random E tilde. And then we compute A the same way, so that it gets through the test. And then we ask What would you? So I think of a number. Yeah. Okay. What would you have said? 0 or 1? 1. Oh, I thought 0 is the case. I do the calculations over again. And then, what's your number?
0.
Ah, yes. I guessed it right. Yeah. Okay. So I also guessed 0. I'm the transcript simulator. He's the cheating verifier, not me, in this game, I assume to be the cheating verifier. So it's the same when I can publish it because I guessed it correctly. Yeah, I don't know what he's going to say, and why I don't know is because he is doing his decision depending on A. He's using A. So I don't know what he's doing. So let's just go back to the protocol here, which is here. The verifier receives A and then chooses E. It could be a random number, but it could be also maybe some hash function with some nonces and with square root of 17 and with 15 digit plus X or a random number times 7 or something. I don't know. Has maybe some good algorithm to do it, which I don't know, but I can guess it with 50%. And why do I have to guess it? Because I cannot give a wrong number here because I have to simulate the transcript. If a dishonest verifier always asks 0, 0, 0, 0, 0, 0, then I have to use that. So the simulator needs. So what's the runtime? I succeed with probably 1/2 in one round and repeat this over again. So you can prove that this is an expected runtime of 2 rounds. To guess the input might take lots of number of rounds, but only with a small probability. And the statements are really from this ZT. And it has the same behavior. Now that's something we have to think about. Why it's the same behavior. Now, this value here is a random number from QR star. So this is really a random number because tilde of b is a random number. And if you multiply this with another square number, we just get a random square number. So this is perfect because A is uniformly randomly distributed. Now B has exactly the property that we need, and it's either the R that we square, or it is y divided by r. So that's r divided by y. So this has also the same behavior. Now the question is, why is this bit in the same distribution? That's an interesting question. Yeah. So because it's like we are actually using this oracle over and over again, and does it change the probability distribution if you go and ask him over and over again? And the answer is no, because this protocol, I'm asking here, given y and a, what would you do? And with 50% I discard the answer, and 50% I would accept it. And each discarded and accepted messages is independent from what he was doing. So he gets a random number. I ask him this with 50%, I would accept it, and with 50% I would reject it. I wouldn't reject it on the answer, depending on the answer. I just reject it on some random number which actually has no influence on the verifier's point of view. So this is really the same probability distribution depending on A, if it shows. And A was not published before. So that's why, it's perfect. But it's also not easy to see that it's perfect because the verifier is depending on A, and A is something we give to the verifier. And if we don't use it, then we have to do it again. Okay, it's more complicated than you think. And it's even complicated without thinking. So this was perfect zero knowledge. This is the best you can do. And so the distribution can be simulated perfectly if you know what the verifier would ask you. The verifier doesn't get any information because you don't need the prover's information to compute it. So sometimes you can't achieve that. So sometimes you have some kind of statistically close zero knowledge. So that is nearly perfect knowledge, but with some very, very small probability, you have a deviation in probability distribution. So that this is not exactly the probability, but it deviates with some small value, which you cannot statistically detect. So it's so close to perfect that you can run a lot of tests and you don't see the difference. Okay, if sometimes you can't do that, and then you have something which is called computational zero knowledge. So sometimes, and so if you look at the first example here, where you actually know that this cannot be computed. You cannot compute A if you see G to the A. So that is not zero knowledge, because the things sent around have a meaning. And do you get K from this computation? And of course you could emulate the communication, but you have no chance to get K, because no algorithm can compute it under certain assumption. And sometimes you cannot produce zero knowledge, but the best thing you can do is you can say that no efficient algorithm can distinguish a simulated transcript from real distribution. So you could produce a transcript, and the transcript looks random, but it's not. But you cannot distinguish it from real distribution by any algorithm under certain assumptions. Okay, so these are three. And the third and the fourth one we're looking into is honest verifier perfect knowledge. And that's something we already have seen. So assuming that we have an honest verifier, I can simulate the distribution. Which means that the honest verifier doesn't learn anything. Possibly a dishonest verifier learns something. So you could change an honest verifier perfect zero knowledge. You can maybe you can correct this by two means. First of all, the dishonest verifier has to prove that he's actually made the honest decision. Have you taken a random bit? Is it really random? Yeah, but that's one way to solve it. And another way is something we see on the next slide, that you determine the verifier. So that means possibly a dishonest verifier can attack the scheme, and you have to check for it, while dishonest verifier doesn't learn anything. So honesty is something which could be bad. Okay, so now, okay, just look back for honest. We already had an honest. Where is it? Here it was in the. Here we had an honest verifier, which was we simulated it here somewhere. Verifier, sorry, can't find the slide. Here, we had already an honest verifier perfect zero knowledge proof, which was much simpler, where we just said, here the verifier will make a random choice, and we simulate that, and then this computation is also like that. So this is much easier to prove. And so that's something we already did. So the next thing we want to do, and we will stay in this, we want to prove that we know the logarithm. Okay, that we know the logarithm of something. Now, in the exercise last time, we learned that there could be some kind of leakage of information. If you look at El-Jamal, I don't know. So you have some G. What is El-Jamal? You encode G to the R, and then you have the public key, which is Y, to the R times N. So that's the El-Jamal encoding, if you remember it correctly. Or if I remember it correctly, I don't know. Now, last time, we learned that we can receive 1 bit of R. And we can even receive bits of M. Yeah. What was the trick? It sounds like an interesting exercise, so probably we'll repeat this next Thursday. So because now we want to prevent what's happening there, but we have to remember the problem, because it doesn't make sense to solve a problem which you don't remember. What kind of problem is he talking about? I don't know. Okay. So this is all modulo P. Okay. Let's talk about square roots and squares, for the difference. So how many square numbers do we have modulo P? So we have P numbers modulo P. 0 is a square number, but we take this out. Okay, forget 0. Now let's look at all the other numbers. How many square numbers do we have? Yeah? Yes, half of it is a square number. Because -1 and 1 always gives you 2 square roots. Yeah? And so that means that every number is squared to another number, and so you can prove that this will result in half of square numbers. Can you test for a square number efficiently? Is there an efficient test which tells you whether it's a square number or not? Probably it's yes, because he's asking this strange way. That's rhetoric. I told you that's also some kind of zero-knowledge proof. Now you have an impression that there is some efficient test without knowing. Okay, I warned you. What happens if I ask you to compute this? Okay, this has a definition, I guess. The definition of this was a to the p minus 1 divided by 2 mod p. Doesn't ring a bell, this symbol? So it could be a Legendre symbol, or it could be a Jacobi symbol. What is it? Okay, let's make a vote. Legendre or Jacobi? Who says Legendre symbol? 1. Okay, who says Jacobi symbol? 2. It's both. That's why it's called the Jacobi Legendre symbol. So it is a Legendre symbol if it's modulo a prime number, and it's a Jacobi symbol if for every natural number. So it's both. So you're all right, You all winners. Everybody's a winner. Only ones who weren't brave enough have lost now. Okay. And this is +1 if it is a square root, and -1 if it's not, and 0 if it's 0. Okay, here this is a square. So this means this is a square root, a square number, sorry. This is which follows from Fermat and Little Fermat and Euler and so on. Okay, is a generator a square number? A square number times a square number makes a square number. Okay. Yeah, so if you take a square number to the third power, you still have a square number. Yeah, so because you can take the root to the third power. So if you have a generator which is g to the 1, 2, 3, 4, 5, 6, 7, and if it's a square number, the generator will only produce square numbers. But square numbers are only half of the thing, and the generator should cover everything. Okay? So a generator will not be a square number. It will be a non-square number. So that means you can test whether this number is a square number or not for free using the Legendre symbol by this definition. And that gives you away the least significant bit of R, because if R is even, then it's a square number. If R is odd, it's not. Okay? So that is the leakage that we have. We have lost 1 bit of information. Do we want to lose 1 bit of information? No. So we have to do something in order to repair that. Okay, so that's the idea of the slide, is the leakage of this 1 bit. Because if you leak 1 bit here, you leak 1 bit of a public key, and then you leak one bit of a message. And maybe the message was only about one bit, which was yes or no. Yeah, and maybe this yes or no is one is odd and the other one is even. One is a square number, one is not a square number. So that's why it's important that we prevent the leakage. So much for the motivation. Now let's do it. Oh, here it says Legendre symbol. Can't you read the slide? So it reads the least significant bit of exponent. So what's the solution for it? So maybe you remember the calculation of secure prime numbers. So we choose a prime number in such a way that p minus 1 contains a large prime number q. So far, so easy. We have done this. How could you do this? You start with a large prime number q. How do you get a large prime number? You look up in the book, or you just take a random number and make a prime number test. Okay, you start with q, and then you take, you check for 2 times q plus 1, 4 times q plus 1, 6 times q plus 1, and see whether this is a prime number or not. Okay, then after doing that, you take a random h and compute g, which is h to the p minus 1 divided by q. Let's calculate this number. P minus 1 divided by q is equal to, we plug it in. So here we plug, oh, sorry, not this. So we plug this in. So we get, actually, it's not easy to draw an arrow here. Nothing is easy here. Okay. What's the result? 2k. Okay. Has nothing to do with a 2k problem, but that's a silly joke. So we have 2k. This is an even number, if you noticed, yeah? So if I take a random number to the power of 2k, what do I get? A square number. So the result will be a square number. So what is g to the power of q? If I take this g and compute the power of q. Well, it is g to the power of 2kq, which is p minus 1. So this should be the same thing as h to the power of p minus 1. Okay, modulo p. So what do we get? H to the power of p minus 1? 1. Okay. So that means we have a number g which repeats after q rounds. And what else do we have? So q is a prime number. So basically, if you have g to the 2, it also to the power of q will be 1. So now what we do is we do not work with generators anymore. We work with these numbers, with g. So first of all, g is a square number. It could be that g is equal to 1, but then you're really, really unlucky to take to regular wrong h. If it's not equal to 1, then you can prove that this is a group of order q, which is a prime number, a group of order of a prime number. And that means that every element here is also a generator. Remember that we had some problems to find generators in the beginning for prime numbers. So we had to test but here it's easy. Every number is a generator. If you have g and you need to generate it, you take g to the 3rd power, which is cool. And we even have a very simple algorithm to get into this one by just taking a random number to this power. So that means g to the a is g to the a modulo q modulo p, which is very nice because I have 2 prime numbers. So on the lower end, I always have an inverse if I have multiply. And on the top, I have an inverse if I do the exponentiation. So both of them, it's basically two prime order cubes communicating to each other. So interaction, so we have basis and exponent have this nice property. So we don't have to deal with the fact that the generator circles in an even round. Now the generator, which we can call this a generator, but it's not. It's a generator for this group. It's circling around there, which is a very nice tool in order to work with. So from now on, we do not take generators anymore because they are maybe mathematically pure and have nice properties and so on. But for doing cryptography, we will always use these kind of generators. They have these two prime numbers communicating with each other. And then we don't have any leakage anymore because G is a prime number, the public key is a prime number, and probably you should, no, that's not prime. So G is a square, Y is a square, and you should choose M to be a square as well. So otherwise you would leak information. So everything is a square and everything is in GQ. Okay, so much for this short interruption. And now let's learn a perfect zero-knowledge proof for discrete logarithms. Okay, so what we do is the following. Now we have this large prime number and we have a subgroup GQ where Q is a prime number as well. And now we have a generator for GQ. And this feels the same way as using with this generator because we just want to prove that we know the logarithm x of y. You just write that. And we know that y is in this subgroup GQ, but we don't have to care about this. So the goal is we want to prove this without showing x. And so what we do is, so first of all, the verifier knows P, Q, G, and Y. So P and Q are these communicating messages. So just to write it down here, that haven't slide. So P is equal to 2 times K times Q plus 1. So similar structure, we choose a random number R, and we send this random number. We don't send this, so we send G to the R, and we send A. So we send A to the right side, and then again we choose a bit E, send it backwards, and now we send R plus E to the X. So this will be modulo Q. Pretend it was from the audience. Why? Because we are working with exponent. Okay, so here we're working with exponent. So we send B to the other side, and then we check G to the B is A times Y to the E. So first of all, this is again a notation for if and else. So let's write it down. If E is equal to 0, then B is equal to R. And if E is equal to 1, then B is equal to R plus X. So, and write this down because we want to see both cases. So the first case, if E is equal to 0, what does the other person get? It gets some random number, which happens to be that G to the R is equal to A. So this is no information which has anything to do with the first one. And in the other case, what you get is R plus X. And R plus X happens to be the logarithm of A times Y. So here we check G to the B is equal to A times Y. And here, this is a question mark. And here we check G to the B is equal to A. Okay, so these are the two tests that we perform. I just noted again within this easier notation where I multiply with Boolean bit. Now, the cool thing is that this is also the knowledge proof that we know the logarithm. And so we can go through that the same way. So first of all, completeness. So if a prover knows the secret, then the verifier will be convinced. Okay. Now for soundness, it's basically the same trick. So again, Eve has a winning strategy if Eve is a cheating prover. And the winning strategy is the following. So we somehow know the choice of a bit. We start with some random b, and now we compute a to be this form. Okay, so backwards. So a is actually not quite the form as the prover side. So what we do is we divide by y if e is equal to 1, and otherwise we just send g to the b. And again, we succeed with probably 1/2. And here is a 1 missing with probability 1. But if we want to make this sure, then we need both. We need two values, b0 and b1. Okay, and what is b0 and b1? So this is b0, and this is b1. And if I have r and r plus x, then I just compute the difference and I get x. So that's revealing. So if a prover knows, if a dishonest prover has both answers for both e's beforehand, then the difference must be x. And so it's much easier to see that this is really the prover knows the secret if he has always the correct answer. Again, what we have done here is this A is a commitment. It's a commitment that either you have multiplied y into it or not. So if you have the logarithm of A, then you have committed yourself to the logarithm and we can check it. Or maybe you have a logarithm of A divided by y, then you commit to that. So this is a commitment that you cannot change A afterwards because, oh, you're asking the wrong question. Just let me rephrase my first answer. That's forbidden. A is carved in stone. You do the commitment, and with A, either you have to show whether you have the logarithm of A, or you have to show that we have the logarithm of A times y. Yes? That's something we'll do later on. Yeah, so you are 1 week ahead. Yeah, so you just invented the Fiat-Charmier heuristic. There is one, yeah, so yeah, probably you're better than you think. or maybe this, yeah, but this is an important point. So E must depend on A, and you can actually make this also with a hash function. There is one weakness in this argument is that this means that the hash function must be good enough. So you're actually relying on the hash function. So if the prover knows what you will do, depending on the answer, then I can maybe change my question and say, oh, he's asking that. So that's a weak point of that. And because I can try out several A's where I have the correct E. That's something we have to work out. So, and this is, if you look for the simulator of a perfect zero knowledge, now just think that this is a hash function. So what we do is we have the simulator, so we choose a random B again, we choose a random E tilde, which is not the choice we have done. Then we compute A, in such a way that it passes the test if it's the correct one. And then we ask the possibly cheating verifier what he would do. And we do this until we get e is equal to e tilde. So now what happens if we have chosen a hash function here? And the hash function that gives us 0 or 1. And we could still simulate the protocol. So the simulator can do that, because that's not a problem for the simulator. But the prover can't do that. Because here, this is done private. The simulator, even if a public hash function, can privately try out several possibilities and do this. But here you have to commit to some A. So you commit to some A, and then you do this. However, you could do as a prover, you could try to do this in advance and check for the correct hash functions. And then you get through it, because if you publish a hash function in advance, then the prover would know it. And the prover would only give out parts where the hash function is known. So we need something more in order to make this secure against a hash function. So that's a problem, because here we only have two possibilities. Okay, but this protocol here is perfect zero knowledge. And I think this is a good opportunity to end this lecture for today, because now we will move on to make this more efficient and how to see how to do the Fiat-Schaben heuristic. And yeah, I thank you for attention and see you on Thursday in the exercise group. And maybe to remember it next Tuesday, what I've done on Thursday. So that would be great. Thank you.